Hello, in this video we are talking about section 6.5, which is approximate integration techniques. In this day 1 lecture, we're concentrating on the midpoint and trapezoid rules. We also reviewed a bit of information coming from Riemann's sums with the left and right endpoint rules. But in this example, we're specifically concentrating on the midpoint rule and the trapezoidal rule. So we're going to use these two rules with n equaling 4, so our number of subintervals, our number of rectangles or trapezoids is going to be 4. We're using this to approximate the integral from 0 to 1 of e to the x squared dx. Notice that this integral is such that we would not be able to apply any of our analytical integration techniques that we have studied in the past. So this is one of the really nice things about approximate integration techniques is it doesn't matter if we have analytical methods that we can use. We don't need to do that. So based on this information that we're going to find, or based on the information presented for the two approximation rules, which approximation do we think is better? So we will answer that at the end. We are first going to start off with talking about the midpoint rule. Well, really for both of them, we need a little bit of introductory information. We have that n is equal to 4. We also have that a is equal to 0, that's our lower bound of integration. B is equal to 1, that's our upper bound. So this means that we can figure out what our delta x is. So that is the width of our subintervals. So that's going to be b minus a over n, or 1 minus 0 over 4, which is very clearly just 1/4. Then this will allow us to find the x values that are dividing our subinterval. So we're going to have the interval from 0 to 1. We are going to have 4 subintervals like so. Our first x value is going to be 1/4 because that's delta x away from our beginning. Then we'll have 1/2 because that's delta x away from our previous value, then 3/4, and then we get to 1 at our endpoint. Each one of these widths is our delta x value. Now, for the midpoint rule, so let me label a few things real quick. So 0, we're going to label as x sub 0. 1/4, we're going to label as x sub 1. 1/2, we're going to label as x sub 2. 3/4, we're going to label as x sub 3. And 1 we're going to label as x sub 5. Sorry, x sub 4. I don't know where 4 went. Okay, so you should always end up with n here as your subscript. Start off with x sub 0, end with x sub n, and then label the ones in the middle accordingly. Now, for the midpoint rule, we need our x bar i's to be the midpoints of the subintervals. So intuitively, we could figure out what these values are. So x bar 1, this is the midpoint between 0, or let's say between x sub 0 and x sub 1. X sub 0 is 0, x sub 1 is 1/4. So the midpoint of that is going to be 1/8. Okay, x bar 2 is going to be the midpoint of the next subinterval, so between 1/4 and 1/2, which is going to be 3/8. x3 bar is going to be between 1/2 and 3/4, so that's 5/8. X bar 4 is going to be between 3/4 and 1, so that's 7/8. So it's perfectly fine to just intuitively figure out what these midpoints are going to be. Oops, excuse me. Having trouble with my arrows there. So it's perfectly fine to figure them out intuitively. If you wanted to use the formula, then x sub I bar is equal to 1/2 of x sub I minus 1 plus x sub I. So in other words, x sub 1 is going to be 1/2 of x sub 0 plus x sub 1, which in this case is 1/2 of 0, plus 1/4, which gives us 1/8. x2 is 1/2 of x1 plus x2, so that's 1/2 of 1/4, plus 1/2, which is going to be 3/8, and so on and so forth. Okay, so you can always use the formula, memorize the formula and use it if you'd like to, or you can simply remember that we're talking about the midpoints. We've already figured out what all these x values are, so might as well just figure out what the midpoint is for each one of the subintervals. Okay, so now we have all of the basic information out of the way, we can actually start finding our values. So then, by the midpoint rule, the integral from 0 to 1 of e to the x squared dx will be approximately equal to delta x times f of x bar 1 plus f of x bar 2 plus f of x bar 3 plus f of x bar 4. So plugging in all of our information, delta x is 1/4. Our function, this is a good thing to point out here, the function is whatever function we are integrating. So in other words, f of x is equal to e to the x squared. So if we take x bar 1, which is 1/8, and plug it in to our function, we're going to get e to the 1/8 squared, plus then we have x bar 2, which is 3/8. Plug it into our function, e to the 3/8 squared. Then we'll have plus e to the 5/8 squared, plus e to the 7/8 squared. Now, if we don't have a calculator, then this is about as far as we can go. If you want to, you could simplify it a little. So you have e to the 1/64 plus e to the 9/64 plus e to the 25/64 plus e to the 49/64. That is really as far as you can go. If you have a calculator, which I would never require you to use a calculator, but if you have one, you can get a decimal approximation so that it means a little bit more. So we get this is approximately equal to 1.4487. Okay, so remember, if we were relating this to area, then the value that we've gotten here for our integral would be the area under the curve. So 1.4487 is approximately the area under this curve, e to the x squared from 0 to 1. Now, of course, that only works because this function is positive, but still, if you wanted to get a meaning for it, you could there. In this case, we're just asked to approximate the integral value, so there isn't necessarily a meaning to it. Okay, so that's with our midpoint rule. Then, if we use the trapezoidal rule, then the integral from 0 to 1 of e to the x squared dx will equal delta x over 2. Then we have f of x0 plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus f of x4. So notice for each one of our interior endpoints, we have to multiply those function values by 2. The first one and the last one we do not multiply by 2, and then we need to divide the delta x by 2. So that's a little bit different from what we have up above. Okay, so delta x is 1/4. We divide that by 2. Remember, f of x is e to the x squared. x0 was 0, so we end up with e to the 0 squared plus 2 e to the f of x1 was 1/4. It's not visible on the screen anymore, but we could scroll up. look at our previous work up at the top here, we're talking about the x values, okay? Not the x bars. The x bars are only used for the midpoint rule because they're midpoints of the subintervals. We just want these x values. So 0, 1/4, 1/2, 3/4, and 1. Going back down to where we were with our formula, we have 2e to the 1/4 squared plus 2e to the, 1/2 squared plus 2e to the 3/4 squared plus, plus e to the 1 squared. So we get 1/8, e to the 0 is just 1. Then we have plus 2 e to the 1/16 plus 2 e to the 1/4 plus 2 e to the 9/16, and then plus e to the first, or just e. Again, if you don't have a calculator, which I would not require you to have one on a quiz or a test, if you don't have a calculator, it's perfectly fine to leave your final answer like this. If you have a calculator, then you can get an approximate value, so it makes a little bit more sense. It's 1.4907. So these are the two approximations using the midpoint rule and the trapezoidal rule. Again, if you don't have a calculator, it's perfectly fine for you to leave your final answers as the exact values, so these two underlined values. We also have to answer the question of which approximation we think is better based on the explanations. And it specifically says to especially think about the graphical representations. Now, if you compare the pictures, associated with the midpoint rule and the trapezoidal rule uses a trapezoid instead of a rectangle. So if you have some function value here, then instead of a rectangle, well, I guess it would be for the midpoint rule, we would have a rectangle like this. So we get that sort of area. But with the trapezoidal rule, we take this value and that value, and we draw a straight line between, and then find that area. So there's no, well, there may be some parts that are off, so that it is an approximation, but it's a lot closer to the curve than a rectangle is going to be. So the best answer for that question then is that the trapezoidal rule is most likely going to be more accurate. That is true in general, that the trapezoidal rule is more often than not more accurate than the midpoint rule. It isn't always the case. There might be some exceptions out there, but generally speaking, the trapezoidal rule is more accurate than the midpoint rule. It's also more accurate than the left and right endpoint rules that just come from Riemann sums. Now, the trapezoidal rule is not always the most accurate rule. There is another rule that we will see in the day 2 lecture for this section, but as far as the rules that we've talked about so far, the trapezoidal rule is, generally speaking, the most accurate one.